W equals F times D. This is one of the most important equations in all of physics, as it represents the energy of motion, work. The equation can be basically summed up as this: work equals force times distance. Therefore, the amount of energy expended is equal to the product of the amount of force you apply and the distance for which you apply that force. Let's take a look. Now, this blue square could represent any object, from anything as small as a hydrogen atom to anything as big as the entire Earth and beyond. M represents the mass of the object. Now, apply this object to empty space. Say we want to make it move a certain distance. Maybe it's a football moving toward a goal, or a spaceship traveling through outer space. The distance it travels we'll represent as d. In order to get the object to move, a certain force has to be applied. All forces have magnitude and a direction, meaning that they push or pull an object with a specific strength in a specific direction. Now the force is derived from the mass of object m, but it is simplest for this scenario to simply represent it as F. Now, to help illustrate the function of these variables, I've stuck them on a Cartesian plane. The simplest configuration of these variables would, of course, be the one where the force applied remains constant, like a spaceship traveling through the vacuum of space. This equation is represented in green. Now I'll throw in a bit of geometry. Say I drew a line here. Suddenly, this becomes a square, and by the rules of geometry, base 1 times base 2 equals the area, and the area of this square would therefore be F times D. Now you might notice the equation for work is also F times D. Therefore, work must equal the area under the equation. So what happens when F isn't constant? We can't just find the area by F times D, can we? Well, desperate times call for more geometry, so here we go. We need to find the actual area under the equation. The easiest way to do this is to simply make an estimation line over the equation. Now we can draw the same vertical lines that we drew before. Look, now we have a trapezoid. Albeit it's not a regular trapezoid, but a trapezoid nonetheless. Now, the equation for a trapezoid is simply this. Well, not very simple, but that's besides the point. So, we did it. Great! Yeah, okay, we estimated the amount of work done. But still, it's an estimation. But what about this? That's a whole lot of energy we haven't accounted for. Somehow we need to get rid of this, make a better estimation. Well, let's see. So, say we have the same equation. Now we apply the same two vertical lines. But the question is, how do we decrease the error in our estimation? Believe it or not, more geometry. So say we add another line, halfway between the two existing ones. So now we can make a line of best fit here, and make another one here. So now what? Well, same thing as before. We've got two trapezoids this time, so the first one is this, like before, and we simply add the other one. So, in principle, you could apply this infinitesimally, line after line after line, and so forth. But every time you add another trapezoid, the amount of time and energy you have to spend goes up and up. Now, there are ways to use calculus to apply the infinitesimal trapezoids in only one or two equations, but of course you have to know calculus to do that. So, the most effective way is simply to estimate, but the key is knowing how much to estimate by. Happy sciencing!